All right. Let's see. Gerald and see. Here we go. Okay. Good evening, everyone. How are you doing? I'm going to
Hang on
mute.
here. How do we turn off the?
Yeah, just turn off a couple things. Bear with me.
Need to turn down the sound here.
All right. I'm going to mute this one. Okay. All right. Here we go. I hope everyone can hear me. Good evening, and I'm Rich Ozer, and I'm here with Gerald McKeegan. And believe it or not, it's foggy tonight.
Imagine that.
Yeah, so this is our 7th attempt at doing live telescope viewing from Nellie. And yeah, I'm going to turn this way so make sure you can hear me. Because if I have both mics on, then you get an echo chamber. This is our 7th attempt, and out of 7 attempts, we've had one good night. So it's really I've come to the conclusion that the reason it took so many hundreds of years for astronomers to learn everything that we know today is mainly because of weather.
Yep. And
if it wasn't for bad weather, we probably would have known everything there was to know about the universe hundreds of years ago. But anyhow, what we're going to do tonight is what we've done in previous nights. We have a number of topics we can talk about, and we've got a number of interesting photographs to show you. What you should see behind us, especially those of you who are tuning in for the first time, this is Nellie behind us, and Nellie is our 36-inch reflector telescope here at Chabot, and Nellie is bowing to the public. And when we get back to normal life one of these days, Nellie will be open to the public again, and you'll be able to come up to Chabot and get views through this remarkable instrument. But tonight, it'll be our background, and that's really all we can do with the telescope. So why don't we start, Gerald, you wanted to talk about the summer solstice, so explain what that was all about.
Yeah, so for those of you who don't know, today was the summer solstice, the longest daylight period of the year. Today, the sun was up for 15 hours and 1 minute. So that's the time from sunrise to sunset. The summer solstice happens when the Earth gets around to where the north pole of the Earth is tipped toward the sun, at noontime. So hang on here, we're dealing with a little problem here. Are we okay?
He says that there's still echoes.
Oh.
I can't explain that because you're not. Sorry, everyone. Making sure this one's not muted. It's got video. This one is muted,
Okay.
and the phone is no longer logged in.
So we're dealing with a technical problem here. Bear with us for a second.
So why don't you continue?
Okay. Okay. So anyway, a solstice happens because the Earth is tipped and its axis is tipped relative to its orbit around the sun. And in summertime, on or about June 20th or June 21st, the north pole of the Earth is tipped toward the sun at noontime. So the northern hemisphere gets the highest sun angle. So our sun today at noontime, at local solar noontime, the sun was about 15 degrees from the vertical. Now, tomorrow, the sun will be a little bit more from the vertical, and it starts its movement back towards the equator, and eventually in wintertime, it will be at its lowest angle. So we call that the winter solstice. So the summer solstice is when it's at its highest angle, and the winter solstice is when it's at its lowest angle. So today is the solstice. Another thing that's going on today just happens to be coincidental. There is an annular solar eclipse going on right now. but you have to be in Asia or Africa to see it. An annular solar eclipse means that the angle of the moon, or I'm sorry, the size of the moon relative to the sun is a little bit smaller than the sun from our perspective. And that's because the moon is a little bit farther away than average. Average distance between the Earth and the moon is about 384,000 kilometers. Today, it's about 389,000 kilometers. So it's a little farther away, which means it looks a little smaller to us, which means it looks a little bit smaller than the sun. So when the moon eclipses the sun, you see the rim of the sun all the way around it. We call that an annular eclipse. And right now that is happening. In fact, it's happening just as we speak for people in Asia and Africa. So if anybody's on who's in Asia or Africa and you're watching it, tell us all about it. All right, so I think Richard wants to get on here now. He's got a really cool picture of a conjunction between the moon and Venus.
All right. I'll turn this. You can see me. So just a few days ago, there was an interesting astronomical event, and I'm actually going to bring it up on the screen here. It's the best way to do this. There we go. Don't need that. We do need this photo. Okay, this is a photo taken in France by an astronomer named Didier Favre, and he captured quite beautifully what this event was. And in the foreground, you see what's called an old moon. It's a moon just as it's about to disappear and become a new moon. And at this point, it would be a very thin sliver in the sky, barely perceptible to the eye, actually. And in the background, you see a very new Venus that is just starting to get illuminated by the sun. And a lot of people have tried to capture this event photographically when it happens. It's very hard to do. It's usually an event that requires manipulating the telescope so it's not going to get overwhelmed by sunlight or a bright sky. And he just did a fantastic job. There was just the right conditions. The seeing was good. You can make out details on the crater, on the craters of the moon. And I just have never seen a photograph quite this good of this conjunction.
You can see the crescent of Venus.
And you can see, of course, the crescent of Venus. So this was just a few days ago, and it was only visible from Europe and the east coast of the United States. By the time it got dark enough on the West Coast to be able to see this, it was already gone. So anyhow, very enjoyable and unusual and rare photograph of the conjunction or occultation of the moon and Venus.
All right. So I think we're going to talk now about a comet.
Yep.
So Comet 2017 T2.
Yep. Here it is. Okay. This, I stole this photograph, and so I got to give credit. And it's from an astronomer named Rafael Esposito. And there's a fair amount of processing that went on to make this image look the way it is. Normally, when you photograph a comet, you see the comet is, well resolved, and it's exactly as it would appear to the eye, and all the stars and anything else in the background is blurred because the comet is moving much faster than anything else. So in this case, he's actually merged the M81 and M82 galaxies, which the comet was passing by in the same field of view, with a photograph of the comet in order to create a composite image. But it's a beautiful image, and this comet has been passing alongside a lot of notable astronomical objects, and these two being some of the most beautiful and bright. So this was something I hoped we were going to be able to look at tonight, but we're going to have to go with the photographs instead. Got anything else to say about comets in general? Or?
No, the comet is now outbound. It swung around the sun and it's now outbound. The comet tail, you can tell which way the solar wind is blowing because the bright comet tail extends in the direction opposite the comet head from the sun. So the comet tail is being blown away from the head of the comet by the solar wind.
Right, and those two galaxies are a famous pair to look at, and maybe if we have a clear night one of these days, we'll be able to put the telescope on them. And they're, of course, much farther away than the comet. They're, 12 to 15 million light years away, whereas the comet is passing through our own solar system right now and is measured in, 250,000 miles here and there, or not millions of light years. So it's quite a distance perspective here.
All right.
And next.
So now we're going to look at a globular star cluster called M3.
So this is like the fourth or fifth time we've brought up a picture of M3 at one of these presentations, but we have something new tonight that a friend of mine was able to capture from Walnut Creek. And this is a photograph from Mike Harms, and he's a member of the Mount Diablo Astronomical Society and has a backyard observatory, and was photographing M3, which is something we've photographed a few times with Nellie and shown you live. Actually, the first time we went live, we had M3 live through the camera. But what he wanted to do was capture it over multiple nights and turn it into an animation. And he found something very interesting when he did that. I'm going to bring up that animation. There we go. If I can find it. Here we go. All right. And let me get rid of this. All right. So I'm going to move my cursor here to various points of interest. And you'll notice that just to the left of the cursor, you see a blinking star. And if you start looking carefully around the image, here's another one, just to the left of the cursor, blinking star. Just to the left of the cursor, a blinking star. Here's another place where there's a blinking star, barely blinking star. This one's very obvious. Just to the left of the cursor again, notice the blinking star. So what's going on here? They're not all blinking, just some percentage of them is blinking. And what this means is that this globular cluster has a high population of variable stars. Now, we think of a star as usually just being a particular brightness night after night, but actually all stars have some degree of variance in them, even our own sun. As you know, our own sun has an 11-year cycle where it gets hotter and cooler and has more activity than less activity. That's a much less extreme version of what we're seeing here, where individual stars are getting much brighter and then getting much dimmer over a very short period of time. So these are all variable stars, and over a few nights, he was able to capture a pretty profound difference. And I had never really known that this was a thing. And when he posted this, I was quite amazed, and I thought he did a fabulous job. So M3, just if you want to know the distance, it's about 34,000 light years away. So it's about, I always figure that's about a quarter of the distance across the Milky Way galaxy, right? You could think of the Milky Way galaxy as anywhere from 100 to 200,000 light years across. This is 34,000 light years away. So I don't know, rule of thumb, anywhere from an eighth to a quarter of the way across the Milky Way for most of the bright globular clusters that we can see.
And these stars are a little bit younger than the typical globular star cluster stars. Most globular star clusters, the stars are very old, more than 10 billion years old. They're among the first stars to have formed in our galaxy. But M3 has quite a few somewhat younger stars, and we can tell that because of the metal content when we look at these stars. very, very old stars have very low metal content, but as newer stars form, they pick up some of the remnants of supernova explosions and dying stars, and there's metal in the gases left over from those events. And so newer stars pick up those metals, and when we analyze the composition of newer stars, we see a lot more metal than we do in very old stars. And it turns out M3 has a lot of what we consider to be second generation stars that have picked up more metal than most globular cluster stars have.
Great. Thanks.
All right.
Last one.
Oh yeah. So
M27.
M27.
All right.
Let's
so
see. Do you also have M57 there by any chance?
Do we? No, I don't. We don't
Okay.
have that. We'll have to
All
save that one for the next time.
Okay,
Alright.
well, let's look at M27. I think last time we looked at M57. M57 was the ring nebula. This time we have what's called the dumbbell nebula, M27. And both M27 and M57 are what we call planetary nebula. And a planetary nebula is caused by a star that's a moderate to low mass star that has reached the end of its life. People tend to think that all stars die in supernova explosions, but that's actually not the case. Only about 10% of the stars die in supernova explosions. So they have to have 8 times the mass of the sun or more in order for them to die in a supernova explosion. Most stars are much lower mass than that. For example, our sun is. And stars that are lower than 8 solar masses die in a much slower process. First, as they get close to the end of their life, they swell up and become red giant stars. And once they're red giant stars, they become very large, 100 or more times their original diameter. When they're that big, their gravitational hold on the outer layers of the star is very weak, and there's a lot of winds going on within the star. And those winds tend to blow the outer layers of gas of the star out into space and the surrounding space around the star. This goes on for maybe 100,000 years or so. And during that time, the star loses quite a bit of its mass. It loses a third or more of its mass to this gas that's blowing out into space. At the same time, it's running out of fuel at its core. And eventually the fusion process at the core stops and the star collapses and becomes what we call a white dwarf. And a white dwarf, if you imagine all the mass of the remaining mass of the star squeezed down into a ball about the size of the Earth, that's where you get a white dwarf. The matter in the white dwarf is what we call degenerate matter. It's highly compressed, and all of the remaining heat that was in the star has now been compressed down to this very small ball, and that makes it extremely hot. And when it's that hot, it emits ultraviolet radiation. The ultraviolet radiation goes out and it hits all that gas that the star was blowing off when it was a red giant. And the ultraviolet radiation ionizes the gas and causes it to glow. And so we see these glowing clouds of gas around the white dwarf. And I'm not sure if we can see it. Point out the
central star here.
That's the white dwarf right there. And all that gas that you see surrounding it is being lit up by ultraviolet radiation coming from the white dwarf. These are very common. There are a lot of these planetary nebulas out in space. They're often very symmetrical in shape. This one has a kind of a dumbbell pattern, but if you look carefully, the gas is completely surrounding the star. Sometimes the gas comes off the poles of the star, so you get a kind of an hourglass or butterfly shape. It varies quite a bit, but it's very common for us to see these symmetrical gas clouds out in space that are surrounding the remnant of a star that was once like our sun.
Most of them are really dim and tiny. This one is particularly nice to photograph because it's bright and it covers a large field of view in the frame of the photograph. So this is one of the easier ones to photograph. You'll notice that some of it is blue, and actually I gotta go with this one.
Yeah,
Some of it is blue, and some of it is red. The blue here is representing oxygen, and the red is representing what's called hydrogen alpha. And this particular planetary nebula makes a great distinction between those different elements in the directionality of the axis. So this axis here is best known for the oxygen, and this axis here is best known for the hydrogen alpha. And I was photographing this last night mainly to see whether I could start capturing those different elements, and also to figure out whether I had my filters in the right slot, because you need an object that can distinguish the hydrogen from the oxygen very clearly in order to figure out whether you put the filters in the right slot on the filter wheel, which I wasn't entirely sure I had done correctly. So,
you mean you had red on the interior and blue on the exterior?
That's what I was very afraid of. But I thought that I would show you the results from my efforts. It wasn't last night, it was actually the night before last. And to give you a good sense of what a 36-inch telescope can do compared to an 11-inch telescope. Gerald, this what you said was a 1-minute photograph?
1 minute photo.
This was a 1-minute unguided photograph with a 1-shot color camera, meaning it was a color, either a DSLR?
DSLR,
okay,
right.
This was a DSLR, just a standard Canon camera hooked up to the telescope with the shutter open for 1 minute. And we got all of this magnificent detail. I have an example here. This is not processed yet. I don't have any color yet because this is the raw photograph. This was a 10-minute long guided photograph with an 11-inch telescope. And if we had done this much time on Nellie, it probably would have blown out the image. So it's really a treat to be able to gather images from this large telescope, because we usually don't have those types of opportunities unless we're part of a university or some kind of professional organization. So anyhow, I thought I would illustrate that.
Yeah, there are actually people out there who get paid to have this much fun.
That's right. Yeah, we have to pay in order to do it. Anyway, I think that's about it. I can go look and see if there's any questions from people tonight.
Do we need to go back to the?
Yeah, let me do that. Let's go back to our full view. See if we could look at us instead. Stop sharing.
Not sure why anybody would want to do that.
Yeah, I'm really not sure either. That's true. Let's lower the volume. All right. Let's see if there were any questions. Somebody was pointing out that it looks like an eye nebula. I'll tell you, there's a couple out there, like the Cat's Eye Nebula, that actually do look like an eyeball, right, that are remarkably like an eyeball, frighteningly so. And maybe in the future, we'll have a chance to look at that live. People thanking us, which is nice. And I am not seeing, if people want to ask questions, now's a good time to post them. If you did already, post them again for me so I could see them come up on the screen. Let's see. People are comparing the sizes of telescopes that they've got. By the way, I want to thank whoever called us tonight and to tell us about the echo chamber. I'm not sure who that was, but it was very helpful to learn that that was still going on.
Probably John.
It could have been John. Yeah. I wasn't sure. I didn't recognize the voice. Yeah. So don't be offended if I said, okay, we got to go now. No, we can't, Rochelle, we can't view live sky tonight because we're completely fogged over, which is a common problem here.
It's a common summertime problem. Yeah.
Jorge asks, what's a traveling star? I don't know. I've never heard of a traveling
Somebody
star.
Google that real fast.
Yeah, I don't know what a traveling star is. What do you recommend as a good tool for astronomical photography? The best all-purpose tool for astronomical photography is a DSLR camera,
Right.
hands down. They're approachable. Most people own them, or not most people own them, but a lot of people own them, and they're not expensive. There's lots of different ways to use them, either with a telescope or without a telescope, to take astronomical photographs. That's a whole subject in lecture series unto itself.
We actually did one of our first programs.
We did, yeah, we did one earlier this year. There's one, I think, on video. In fact, there is an astrophotography seminar that I did for Chabot that's in the video archive on Facebook. So if you want to get an introduction to using cell phones or DSLRs or CCD cameras for astrophotography, go back and take a look for that video. How much daylight do we lose every day now? Well, we stopped today. Now it's going to start.
We'll start losing daylight.
Now we're going to. It says how much do we lose? Oh no, that's what he asked. How much daylight do we lose every day now? So it's what? It's like five or 10 minutes.
No, it's about one. Initially, it'll be about 1 minute a day.
Okay.
But then it'll get more and more as time goes on. But initially, it's only about 1 minute per day.
Oh, as that angle increases, then we lose more and more time.
Because the other thing that happens, if you look where the sun rises and the sun sets today, they rose north of straight east, and they set, or the sun set north of straight west. But as we get into the fall, the position at which the sun rises and sets gets closer and closer to east. That means that the actual arc of the sun is shorter.
That's right.
So as we get closer to that point, the amount of time between each day, the amount of sunlight each day increases or decreases, as the case may be.
Virginia asked, what's the brightest star I saw last night? Well, there's a number of possibilities, Virginia. Probably what you were seeing, what I've been asked, all week about, is, first of all, Jupiter was very bright at around 11:30, 12 o'clock p.m. And that would have been in the southeast sky. And the other very bright object much later, or towards early morning, Venus was up. And then if it was earlier than that, like 9, 10 o'clock at night, then you may have been seeing Vega or Arcturus. But Vega was also exceptionally bright, it seemed, the other night, because a lot of the other stars were obscured by high altitude clouds, but that part of the sky was wide open. And so Vega appeared quite bright.
Yeah, if you're out, like, say, 9:30, between 9:30 and 10 o'clock, and if you look almost straight overhead, there's a bright yellowish star. That's the star Arcturus. At that time, if you look off to the east, you'll see a bright bluish white star, and that's Vega.
Right. The 36-inch scope, this was to Tracy's question. The 36-inch scope is the one that's behind us. That means it's 36 inches in diameter, right? So it's our largest instrument here at Chabot. When I was talking about the 11-inch, that was a C11 Celestron, just a standard consumer telescope that I happen to have. And that was the comparison I was making.
Astronomers refer to their telescopes by the diameter of the telescope.
Not the length,
So when we say 36-inch telescope, that means the diameter of the primary objective, in this case a mirror, is 36 inches in diameter. Richard's 11-inch telescope has an 11-inch primary mirror in it. You'll hear amateur astronomers talking about 10-inch and 11-inch and 14-inch and 8-inch and so on and so forth. They're all referring to the diameter of the primary mirror or the primary lens, depending on the type of telescope.
Mark wanted to know about the image data for that shot of the moon and Venus. Yeah, I'll tell you, I'm going to look for that. I have not seen the details on that, because I think that would be very interesting.
I'll bet you it's a combination of a couple of images.
Yeah,
with
I
different
would think so.
exposures.
It might have been video.
Oh, that
It
too,
might have
yeah.
been stacked video. In fact, that would be my guess.
Yeah.
That way he could pull out just the ones that are really sharp. I'll tell you what, Mark, if I do find that out, I'll private message you on Facebook and let you know. I think that's about it. Thank you all for your questions. They were very good questions tonight. And until next time, I
Yeah,
guess we're doing
yeah.
this next week. We will not be doing this on the 4th of July.
Right.
So
You're just going to have to go out and watch fireworks.
you have to watch
you know.
fireworks, right? Hopefully it won't be foggy and be shooting fireworks into the fog.
Probably won't be foggy.
Probably, that's right. The night that we don't do it will be the clear night.
Right,
That's undoubtedly the case. It usually works out that way.
Yeah, that's near full moon as well. So yeah, that's one of the rules up here is that we have clear nights when we have a full moon, and it's foggy when we have new moon.
Yeah, well, if next week, if it is clear, we will be trying to get some live shots of the moon, and that'll be the obvious target for us. We'll see what happens.
Yeah, now you want to tune in again next Friday night. We have a guest speaker from the Lawrence Livermore National Lab who will be talking. That'll be at 8 o'clock next Friday on the Chabot Facebook page.
All right. Thanks, everyone.
And don't forget to donate to Chabot. We need the money.
Take care now.